Log on, tune in, find out. Another good idea from Cambridge.
We probably ought to get started. For those who don't know me, my name's John Thuber, and I'm chairing this morning's session. First of all, can I just check, is our second speaker here Rachel Warren?
I got an email from her saying she was going to show up with seconds to spare. Well, not exactly.
Okay, check again for the phone because I can hear. Yeah, thanks. Yes,
they really have to be switched off and not just in silent mode.
Okay, so as Michelle says, switch your phones off, otherwise the recording equipment picks it up and amplifies the signals, and we get a nasty, distracting buzzing. Hopefully, you've had a chance to read the notices, so I'm going to switch these off now. Figure out how to do it.
I'll do that one, John.
Betches, yeah. Okay, so I think without further ado, let's kick off with this morning's first talk by Peter Cox with the intriguing title, Turning Noise into Signal.
Right, thanks very much. Is the microphone working okay? The back? Right, so, not sure. It is on. It's on. It might need to be a bit higher. No, you don't need a microphone, Michelle. You're right there. Okay, well, they'll tell me. Okay, so this is, well, first of all, great to see so many faces back here. I'm sorry I arrived a bit late. We had a sort of combination of a domestic issue with, I was trying to get contracts signed on a house by today and getting proposals in, which is, it's arguable which is the more urgent thing, but none of them more interesting than being in here, unfortunately. So I'm glad I'm here now. This is a title I unwisely came up with when I was here a couple of weeks ago and we were having a lot of exciting discussions over coffee. Doesn't even have climate in the title, which suggests it's going to be a lot more general than it actually is. But I wanted to just sort of summarise a few bits of work that have spun out that I'm aware of anyway, and this is a small part of the programme, but the bits that I'm aware of that are work in progress but I think are interesting, and all of them kind of relate to this idea that rather than throwing away variability in the climate system, that we can use it as a very good constraint on sensitivity, and sensitivity is the thing we're worried about with regard to climate change. So I'm going to kind of rather superficially scan across three separate possible applications of that general idea, and it is a very, it's a deliberately kind of broad and shallow kind of focus. So a number of people have been involved in this. I've just named a few here. Chris Huntingford, who's here, Ben Booth, who's not, Roddy Dewar, who has been here working on MEP stuff, and Tim Lent. I don't think Tim's here today, but Tim is working on the tipping point stuff. I'm going to talk a bit about things that they've at least got going in my mind, and of course a number of them have spoken already this week, and you can see their seminars on the during the programme, and you can see their seminars on the web. Okay, so the outline, there's three bits to this. First of all, there's been a lot of talk this programme about the application of maximum energy production principles, if you like, this idea that certain aspects of the climate system, in fact certain aspects of reality, especially turbulence, may maximise something like the rate of entropy production. And there's been debates this week, this programme, about the theoretical basis for this. There's still some debate about this. Bottom line is it seems to work unreasonably well for certain aspects of the problem. I'm going to give one simple example, very simple example as a kind of motivator. The second thing is rather closer to what I normally work on, which is how do you constrain how the land carbon sink, land carbon stores will respond to climate change. And this is a big issue for future climate change. It's also a big issue in response to variability. So for example, at the moment, 2010, we have the most severe drought in some respects in Amazonia recorded. And the question is, how does the carbon store in the Amazon forest respond to that? And what we've been doing is just essentially using some ideas that come out of very simple stochastic climate models and applying them to the carbon cycle response to climate problem. So it's very rudimentary mathematically, but it seems to me to give a useful constraint. I'll just talk briefly about that too. And then finally, some very early work that we've been doing looking at this idea that the possibility, at least in some models, that the Amazon forest could die back under global warming scenarios. And in this case, these constraints are too linear and you need a more non-linear approach. So we're going to try and apply some of these climate tipping point time series analyses to see whether there's any precursors in the models at least. If we could identify such precursors, of course, we could potentially develop an early warning system for the real world. Happy to take questions as we go through if there are any. Okay, so first thing, maximum energy production applications to climate. And we've been very lucky to have Roddy Dewar here for a while, Robert Niven's here somewhere, just here, both working on the sort of theoretical basis for this. And some interesting debates between these two guys that I've only just beginning to understand. You only live within work within a few miles of each other, don't you? But we have to bring you here to talk. Tim Jupp spoke about an application or a slight extension of these maximum energy production models for the equator to pole heat transport. And Jonathan Gregory earlier in the program spoke about trying to apply this with limited success to GCMs. But I just want to give a brief rundown again of this, of why we think it's useful and how the kind of fashion swung backwards and forwards on this. So in the 60s, Ed Lorenz, and we'll come to another Lorenz shortly, suggested the climate system maximises work. That turns out to be a related issue. Garth Paltridge, rather magically, in papers that you've heard talked about a number of times in 75 and 78, develops a climate model, a zonal climate model, that has no dynamics in it at all and appears to reproduce cloud cover and temperature variability zonally in a rather magical way. And it turns out that there is some magic in this. It's not just maximum energy production, but maximum energy production is part of it. And then Ralph Lorenz, who's no relative Ed Lorenz, then re-energized this debate by applying this MEP approach, in fact a simplified version of Garth Paltridge's approach, to pole to equator contrast of temperature on Titan and on Mars, and suggested that he could get this Titan gradient within the observational bounds, which are quite large, with this MEP approach, whereas he couldn't with scalings that were based just on dynamics. So this got people heated, literally, about the whole thing, because it looked like actually you could do a better job by throwing away the dynamics and replacing it with MEP. And here's the Lorenz model. Very, very simple. And the reason I show you this is because I'm going to achieve the great thing of making something even simpler. Maybe it's a great thing, maybe it's a bad thing. Essentially, there's just two boxes in this model. So whereas the original Paltridge model had zonal variation, this has just got two boxes. It's got a tropical box with some temperature T0 and a polar box, and it's just trying to work out what this equator to pole flux F should be. And the assumption is that this flux F will maximize the rate of entry production by itself. And that depends on the size of the flux and the temperature differences between these two boxes. So as the flux goes up, you tend to increase entry production. So you would have said that's a large flux case, but as you do that, you reduce the difference between the tropical and polar temperature, and therefore reduce entry production rate. And the real state is somewhere in the middle. Okay, so the entry production rate in these simple models is just the flux times the difference between the inverse temperatures. Very simply. And when Lorenz applied this to Titan, he found he could do a decent job on this is the equatorial temperature and the polar temperature. And this occurred, the best fit occurred when the entry production rate by this zonal heat transport was maximized. Okay, so the maximum energy production fits the observations best. And he subsequently looked at, Paltridge had already shown it more or less works for Earth. And he subsequently also looked at Mars, and with some modifications for change of state of CO2, managed to get that to work as well. Tim Jupp, I'm not going to say very much about this. Tim Jupp, in the first week of the program, spoke about a model where we tried to extend this to look at limits associated with rotation rate. And Peter Reed spoke about related issues in a talk, in a seminar, and basically found that this rotation rate was not high enough on Earth for rotation to limit that entry production flux. In other words, the rotation rate was low enough that you could reach this MEP state. But it wouldn't need to be much larger for the dynamics to be a real constraint on what you could do with regard to entry production rate. And that's quite interesting because in the past, the Earth probably was rotating faster. So there is a question about whether, if you look back in geological time, there would have been a period where you couldn't reach the MEP state without reference to this constraint. And that's maybe something that we'll come back to, not here, but in future work. Sure. Right.
Highly constrained by rotation.
The heat transport doesn't seem to be, and it's a very simple model. I mean, basically it's got a Coriolis term that relates to the drag, and the drag relates to the heat transport. And in that model, what you find is there are regimes where rotation matters, and there are regimes where it doesn't, and it turns the Earth just on the boundary, at least with regard to that model. Now, I guess from speaking to Peter Reid, I think he's also seen that in some of his experiments, in that if you spin it up a little more, then you start to see different structures that do constrain the transport. It might be that our model's too simple, but based on that model, it sort of explains why these models with no dynamics work, at least in these two box models. But they wouldn't work if the Earth was spinning a little bit faster. Okay, so Tim Jupp described this as dangerously seductive, this whole MEP stuff, and I think he's right. But I replied by saying, well, it's quite nice to be seduced sometimes. And this is my ultimate climate hero here. So let's be seduced just for a little while. It's a bit early, but let's do it anyway. So what I wanted to do, and what Roddy Dura and myself and a number of others have been trying to do, is to turn this whole thing into the vertical, because in a way, if MEP applies, it's likely to apply to turbulent fluxes that are fast to react to boundary conditions, I think. So I think it's more likely to apply to turbulent fluxes and convective fluxes than it is necessarily to zonal transport, which is controlled by all sorts of slower processes. So what we asked ourselves was, could we predict this turbulent flux, which is the sum of the latent heat and the sensible heat, as a function of the atmospheric radiation balance with a very simple model. And later on I'll talk very briefly about the fact we're trying to extend this to look at cloud cover over the oceans, because the thing is about these MEP principles, they are very tightly constrained. I mean, you can prove them wrong very easily because there's not much wiggle room in them. If you insist on an optimization, you even have to say that I've got the wrong constraints or the principle doesn't apply. Okay, so we're going to try and predict this turbulent flux, just the amount of turbulent flux that you get for a given amount of net shortwave coming into the system. Okay, and I'm going to use a model that I get my students to look at, which is called the leaky greenhouse model. Some of you may know it. It's about the simplest model that shows some sort of greenhouse effect. So you imagine you've got some atmosphere with an emissivity epsilon, and you've got some surface with an emissivity of 1. There's no reflection in this atmosphere, or it's just a transparent atmosphere, so there's absorbed shortwave at the surface here, which is also the shortwave coming at the top of the atmosphere. And there's long wave coming out of the surface. There's long wave coming down from the atmosphere and going out to space. And this is the leaky bit. So as the window closes up, as epsilon gets larger, the amount of surface long wave that goes out reduces. And this is a very simple model of the sort of greenhouse warming of the atmosphere and the surface. Now what we've done is just add a turbulent flux. Very simply, we said there's another flux coming from the surface that's not a radiative flux, obviously. It's associated with turbulence convection. What is the F that maximizes energy production by that F? And you can see it's a bit similar to the zonal problem. And if I crank up this F, I increase the energy production rate, but I also reduce the difference between TA and TS, which will reduce the energy production rate. The question is, does it fit the observations? So I put model in inverted commas here because it's really not enough to be called a model, really. But so this is the top of the atmosphere budget. This is the net short wave, outgoing long wave in the window region, and the outgoing long wave from the atmosphere. And in the surface energy balance, we've got the same short wave at the surface, sun warming from the atmosphere, balancing the long wave from the surface and this turbulent flux. And F is assumed to maximize the rate of entry production, ds by dt, and that basically means we're looking for the maximum of this thing here. And you can see, of course, that these things are both dependent on F, so there will be some interplay between them. Okay, and this is what it looks like. Roddy Dura can actually solve this analytic, but I have to do it on the computer. So this is emissivity here. So as we crank up greenhouse gases, we go in this direction, which is quite interesting. And this is the turbulent flux normalized by the absorbed shortwave. Right, so it's the fraction of the shortwave flux that's converted into convective turbulent energy. And what you're looking for here is the maximum. That's what the MEP principle says, is that my system will sit on this maximum here. And let that's basically what it predicts. So there's a pretty tight prediction here, and it's a prediction that relates to how much turbulent flux is relative to the absorbed shortwave against something like atmospheric emissivity. This is something we can check. We haven't checked it yet because it would spoil our fun, but that's something we can definitely check. Okay, and interestingly, and this is why you must be able to solve it analytically, the turbulent transfer coefficient, so that's basically the flux divided by the difference in the temperatures, is linear, very nearly linear in the emissivity. So basically what this says is that if I crank up CO2, I should get an increased efficiency of transport of the heat. So it's a prediction of how turbulence varies with atmospheric emissivity. Okay, any questions? Maybe it's not so seductive after all. So we can turn this into, in order to compare with other things, I've converted this emissivity and infrared optical depth, which is basically looking at the exponential. And this is what the two-box MEP solution does. So as the emissivity gets larger and larger, or the optical depth gets larger, asymptotes to something like 0.6. So 60% of the shortwave in the absolute limit would be converted into turbulent transfer in this model. And this is two radiative convective model solutions from a paper by Lorentz and McKay, 2003. These don't assume MEP. And this is an MEP-based solution on a much more complex vertically resolved model, which has to assume things like gravity. We haven't even told this model that there's any such thing as gravity that you have to overcome for convection, which is rather bizarre. This is where the Earth sits, and so we're right and everyone else is wrong. That's all you need to know. and this is roughly where Mars is, but we don't know very well. Essentially, you have this is a very well defined, for the structure of the model you assume, this is a very well defined thing that you can test. Okay. What we're trying to do now, I mean, that's all very well and good, and there's many other ways you can get the turbulent flux roughly right, including the way we already do it. But what would be very interesting is to see whether we can get some constraint on cloud feedbacks from this. I mean, could we, for example, look to see whether there is a cloud cover amount and height that maximises energy production by turbulent fluxes? And Roddy and myself are looking at that at the moment. The sort of thing that you're interested in is a paper that I just discovered, which has been out for a year, so I should have discovered it a while ago, about cloud feedbacks and sea surface temperature. And this is Amy Clement et al., 2009. So this is showing that the cloud cover tends to go down when the sea surface temperature goes up. And we do actually see that in very simple models of MEP-based models of the convective heat transfer. But we don't get large enough sensitivity, and that may be because MEP doesn't apply. It may just be because our models are rather too simple yet. It does go in the right direction, though. Any questions? Okay. I'm going to change gear. So my main business has been to try and understand how the carbon cycle, particularly the land carbon cycle, responds to climate. And this is a relevant problem for the issue of future climate change. The basic problem is that we're putting CO2 into the system through fossil fuel usage and also through net land use change, things like deforestation. And that part of that's absorbed by the ocean, part of it is absorbed by the land. The remainder goes into the atmosphere and affects the climate through the greenhouse effect. All very well and good. In the last 10 years, people have gradually been putting in the feedback from climate back to those stores and to those sinks. So the climate changes has an impact on the solubility of CO2 in the ocean, vertical mixing, and possibly the circulation, things like the thermohaline circulation, which will impact the ocean sink and therefore change the amount of our emissions that remain in the air and affect the climate. And even more so with the land, you've changed the climate, you've changed the rainfall patterns, you change respiration rates, you maybe change fire frequency. You might also expect to see a change here. And so models in the last IPCC report, some models did this. In the next IPCC report, pretty much all models will do this. And as is the case, whenever we put in a new process, we just explode the uncertainty. This is just a feedback. This is from a paper by Pierre Friedlingstein, intercomparison paper. This axis here is the difference in atmospheric CO2 that derives just from the climate change, right? So this is the extra CO2 you get because the climate change suppresses the ability of the land and ocean to take up CO2. This is the Hadley Centre model that I was responsible for developing, which is a very high feedback. So just to get these numbers, this is about this is 270 parts per million extra CO2 because the climate is suppressing uptake. So it's it's about the equivalent to a pre-industrial level of CO2 extra. And these are the other models. Now they have lower feedbacks, they're all positive. In the next IPCC report, there will be some down this side because in climate prediction, we always have to increase uncertainty. That's the law in these parts.
First law.
That's the first law of climate prediction, that uncertainty can never go down. So, yeah, we should go. This is one of the reasons why there was a big difference between the Hadley model and the others, and it's related to this issue of, oh dear, I must have that on timer. It's related to this issue that in the Hadley model and one or two others now, drying is sufficient to suppress the forest, cause it to die back, and it releases extra carbon from the system. And in this case, what happens is that the forest is reasonably healthy until about 2000 or a bit beyond 2050 actually, and by the end of the century it's really in a lot of trouble. But the difficulty is it's a very model dependent result. This is from a World Bank report. This is a paper by Anya Ramig from Potsdam Institute. And what you've got here is a single vegetation model. This is different from the one that we used in the Hadley model. This is the LPJ model, Lund, Potsdam, Jena model, which is widely used. This is the simulation of the Amazon forest in the contemporary period, in the current period. This is the simulation 100 years later. And the thing to notice here is in the Hadley Centre model, because of the drying, you get this huge reduction in forest cover with some savanna that's light green and some woodland. But in other models, like the NCAR model, it's actually a greening. It gets wetter in those models. So we don't even actually know the sign of the rainfall change in these models yet. And therefore, we don't know the sign of their sensitivity to climate change. But the observations do tell us quite a lot. These are some slides I've taken from the Global Carbon Project, which you can download, and this is updating the budgets of carbon, the carbon budgets annually, getting best estimates of them. This is the standard, often shown more on a lower record, updated here. So this is the seasonal cycle in CO2, and this is the annual variation here. These annual variations tell you about the sensitivity of the carbon cycle to climate. Someone's got a phone on. Right, this is the main reason why the atmospheric CO2 growth rate, which is shown in this blue curve, is so variable. The emissions don't vary anywhere near as quickly. Even economic downturns aren't enough to produce these sort of variations. So what we've got here is the CO2 emissions we're putting out through fossil fuels and deforestation. This is what's showing up in the atmosphere. And the difference between the two is the uptake of carbon by the ocean and the land. I will come to something that's relevant to this program in a minute. When you do forward modelling, what you end up suggesting very strongly is that interannual variability is totally dominated by the land, and it's totally dominated by the tropical land actually. So that interannual variability is telling us the one thing we need to know. We normally throw it away. We normally just smooth it out. And in that sense, it's a bit like applying a fluctuation sensitivity idea to the climate system itself. It's this sensitivity to climatic anomalies. This is the Pinatubo anomaly here. This 98 El Nino that is driving this sensitivity of the land carbon sink, and that itself is telling us in a roundabout way what we need to know. I'm suggesting, right? And people have tried to do this, including myself and Chris Jones. What you find is that if you detrend that growth rate, you get a growth rate of CO2 anomaly. And positives here mean that CO2 is going up faster than expected. Negatives means it's going up slower. And you can find that if you flip this to the Nino 3 index, which measures the state of El Nino, you can do a pretty damn good job of fitting this. So there's a very strong correlation between tropical variability and CO2 growth rate, which implies that the tropics, and in fact the tropical land, is the main tail that's wagging this dog, this CO2 growth rate dog, as we like to call it, technically. It's strange thing is we generally throw this information away. For example, when we were doing the Friedlichstein analysis, we were looking at the long-term trends and we're trying to separate the carbon response, CO2 response from the climate response. And we thought, well, all this noise just gets in the way. But actually the noise is the thing that allows you to separate these two things. So this is my very snappy title for the next bit. Interannual variability of CO2 as a constraint on the sensitivity of tropical air and carbon to climate change. And this is work that's been going on with Chris Honeyford again here and Ben Booth from the Hadley Centre. Okay, so this is the sort of thing we're trying to do. This, yeah.
Just on that last slide, was there a band of red for the new?
Oh, that's because the fit wasn't perfect. So this is basically my error bars on the fit. The reason
it looks like the linear 3 index. Why did
yes.
the linear 3?
Well, in a sense, yeah. But all we've done is done a linear regression against the Nino 3, and the reason we did that in this case, Tim, was because we wanted to highlight the fact that volcanoes take you outside of the bounds that you can explain with the ENSO variability, and Pinatubo was the largest negative anomaly of all. But yeah, I will come to that shortly. We've got a slightly more sophisticated way of doing it. You'll be pleased to hear now. Okay, so this is the sort of problem you have. Here's a simulation. This is from the Max Planck Institute model for a change. And I'll show you this one because this is one of the ones I can fit. Okay. So this is the tropical land carbon sink. So where it's positive, it's a sink, and where it's negative, briefly here, it's a source. For a scenario, a standard scenario, it's an A1B emission scenario, as simulated by this model. And what you want to know is, well, actually what you'd like to know is, can I predict from observations this sort of behaviour, this slowing down of the sink? I mean, even in this model, there's no dieback in the model, but this is a very significant reduction in the sink efficiency because CO2 is going up and up all the time. In order to do that, you have to break down the response into response to CO2, which is essentially how does the land carbon sink respond to CO2, which is related to how plants respond to CO2 in terms of fertilisation effect on photosynthesis. And this is in this model is a fairly smooth monotonic increase related to emissions and a response to climate change. And this is the local warming. We're just going to see climate here and index it by the temperature change. Not sure how well you can see that at the back. Can you see that all right?
Sort of.
Sort of, okay, good. Sort of's enough. It doesn't warrant any more than that. So these are rather similar, and you can see that there's obviously, if you want to break this down into this and this, there's going to be a lot of degeneracy. And this is the way we'd normally do it. This is a decadal running mean here to get rid of the noise. Now, if I put the noise on, it's huge, right? I mean, basically, the signal is pretty much all noise. This is huge variability. This is a model that doesn't have the largest variability of all. It's got quite large variability. This is from a climate model, right? So it's not from the observations. And then if I put the noise on the temperature, you can see it is the interannual variability that splits apart these two dependencies. And yet that's the very bit that we normally throw away. So what we're going to do now is we're going to use this red line here, which no one can see, but there is a red line here. And we're going to look at the anomalies relative to that and just basically detrend the thing and see how these relate to one another. Okay, so this whole problem is degenerate and has been degenerate unless you include the interannual variability. So we're getting rid of the one thing that we needed to use, I would argue. Okay, so I detrend the land uptake, and we're just going to look at the period where we've got data. So this is where the Morna Lower record spans, 1960 to 2010 roughly. So we'll look at 1960 here to 2010 and detrend it. And this is what the anomaly in this model looks like. So the years you have to treat with, they're just, there's a nominal years here. There's no reason why the El Nino should line up, of course. But these are related to the equivalent of El Nino events and La Nina events in this climate model. And if I then put on the temperature variability in the tropics, it's hugely anti-correlated. I mean, you can't quite see this, but every time there's an up, there is a down here. And the scatter plot shows that. And this is not peculiar to this model. It's seen in all models, and it's seen in the observations, although rather less directly in the observations. So this is a pretty good fit. Detrended temperature against detrended land uptake. And zeros here. So here we've got anomalously large uptake and anomalously large release of carbon. So as far as the interannual variability is concerned, these models there's a lot of detail in them, but they produce something pretty simple. There's a linear response between the temperature variability and the sink variability. And I can do what Matt said I shouldn't do again. and I just produce this fit, and this red line, which you also can't see, is a very good reproduction of that anomaly. So basically, the only thing we need to characterize the sink in this model in terms of internally variability is the way the temperature varies and some sensitivity coefficient. And in principle, you get that sensitivity coefficient from observations. Now, the tricky bit is you want to separate out the temperature, the climate variability from the carbon dioxide variability, and you can do that. So now you say, I'll put the trend in climate back in, and I'll come to the model we used to do that. And what I've got left over is my CO2 variability. So this is the CO2 dependence of land uptake against CO2 concentration, and it's a fairly well-defined response that turns out to be, to very high accuracy, logarithmic in the CO2 concentration. This is a rather peculiar thing because these models went away from a logarithmic dependence. In the old days, they used to have a thing called a beta factor, and models like Magic would say, well, let's call it logarithmic in CO2. And people who work with plant physiology said, that's nonsense. Don't put that in. So we put in these rather complicated plant photosynthesis models, and out pops the logarithmic dependence on CO2. I think I've got to apologise to Tom Wigley, but I'm not going to do it. And I don't know why that is yet, but it is an amazing thing that these complex models end up with very simple responses. So, because it's like that, we can come up with a pretty simple model of the tropical land carbon sink. So, it doesn't look simple yet, but it is. So this is the change in land carbon in the tropics from some nominal initial state. Let's call it the pre-industrial state. So this is a linearization. This is our linear dependence derived from internally variability on the warming in that region. And here's our logarithmic dependence on CO2. I've put a normalization factor in here because I want it to look like previous studies that have a slightly simpler model. And what we've got here is a lag term. This is the thing that we've never had before, which is basically allows us to relate short timescale variability in climate to longer timescale responses in the carbon cycle. So this TOR is a characteristic timescale of the land carbon cycle, and you can relate it to its initial state. It's basically the turnover time of carbon in the system. Okay. Now, in the case where TOR is small, or where you run the system for a long time so that this term is much smaller than the long-term trend, and the CO2 hasn't changed very much, this reduces to a previous model, the one that Friedlingstein used, which is just a linear quasi-equilibrium model that says the land carbon storage change will be proportional to some factor related to the change in the CO2 plus some factor related to the change in temperature. And that's been rather a powerful way, at least with these complex models, to separate out this sensitivity from that sensitivity, but it's necessarily dependent on the scenario you use because it doesn't take any account of rates of change. So we can extend this now with this rather more, slightly more complete model. This is partly motivated by very simple stochastic climate models like the Hasselmann model. Because if you think about the Hasselmann model, you'd have the temperature here, and this would be some sensitivity, and a temperature change here, and on the right-hand side here, there'd be some stochastic forcing related to temperature variability, say, from the atmosphere.
Excuse me, David.
Yeah.
We got confused one thing.
Yeah.
Is T, the temperature, is it global temperature, tropical temperature, or Nino 3.4?
This is actually, sorry, yeah, I wasn't clear on that. This is actually the tropical temperature. So what I'm taking here with the data is tropical and subtropical. It's 30 north, 30 south means over land. So all of these things apply to land means 30 north to 30 south. Yeah. Tim?
Well, since we're on that point,
Yeah.
I mean, you showed earlier on that, about the Amazon dying off depending on the rainfall, whether, at CM3 has the rainfall
Yeah.
or not. So is this temperature a proxy for rainfall, or is it really temperature?
I think it is a bit of that as well. I mean, I'll show you it doesn't work so well for Hadley. It works for the other models quite well. I think the thing is that in most models, when you don't push them too far from their pre-industrial state, and maybe there's good reasons for this, the warming pattern and the relationship between the warming and the hydrological change is not so different in the climate change, as long as it's not too severe, than it is in, say, ENSO. So I guess in some sense the models are projecting onto that dominant mode of variability. That's why I think it works, because there's no other reason why it should. You're absolutely right. I mean, in a sense, these systems are more sensitive, probably, to rainfall change than temperature. But it seems we can index them. Right, so, and what was I going to talk about now? Okay, so this is this Max Planck Institute model again. The white here is the actual model output, so with this large variability, and the sink growing, but actually saturating slightly here. I've fitted the model over this, that simple model over this Morna lower period, so there's a pretty good fit here. And then all of this is reconstruction, right? I mean, I have to know the model temperature, but basically what we're hoping is that the Morna lower record already tells us what we need to know, actually. We are going to put ourselves out of business, but it'll be fun doing it. And it works for this model at least. And if I then look at the integration of that, then I've fitted this model here, then I'm going to do a reasonable job here. And that's less impressive in a way because it's not a particularly nonlinear response. This, I think, is impressive because we've made an assumption that there is no nonlinearity in the climate response and that the CO2 response is logarithmic. And this model that's doing all sorts of things like the things you mentioned, Tim, lots of variability going on in the tropics, changes in maybe the position of the ITCZ, it still can do a decent job of working out.
Can't it saturate when you sort of get, you run out of a source?
Yeah, so what this doesn't do, I mean, if you really had a very severe source of carbon, what it wouldn't do is to say you've just run out of Amazon forest. And that may be why it doesn't work for one of the models. Okay. Now, fine, so I can then look at the other models, and there are about 6 GCM-based climate carbon cycle models, and I can fit them to that same period, and generally they do an okay job. So this is the NCAR model, IPSL. The one it doesn't work for is the one I wanted it to work for, which is the Hadley Center model. And this may be for the reasons that you were suggesting, Tim. Strangely, I can get this to work, but I have to assume that the timescale for the carbon cycle system to respond to the climatic anomaly is very short. So I have to kind of go to a limit where that TORS term is 0, and then I can get this turnover, but it's not a very honest thing to do, so I'm trying to work out why that is. So what it does get is a kind of saturation. I've only told it this again. It gets a saturation, but it doesn't get this turnaround. So it can't reproduce the strong nonlinearity in this particular model. It does a decent job in the others. So, well, okay. Any questions?
So does that correlate with the fact that the Hadley model destroyed the Amazon forest?
Yeah, that's what's going on here. So this is the dieback. So carbon accumulating for a while in the vegetation soil and then coming out rather abruptly. And what you'd like to be able to do is to work out how long this record has to be to know that was going to happen without actually ever seeing it. Yep.
Excuse me, but you're talking about the Amazon, but you were saying before that you were using the entire tropical land. I mean,
that's true.
Are you assuming that the Amazon is dominating everything, including Africa and...
Well, no, I'm not. Well, I am. In this model, that's certainly true, because in the models, of course, we can tell what the relative contributions are. It's just that we're trying to boil it down to something that the existing observational data can tell us. And it turns out that 30 north, 30 south land carbon is the intraannual variability in the monolayer record. So you're right. You wouldn't be saying that the Amazon in particular was in danger. You'd be saying that the tropical land carbon sink would be in danger.
And I'm wondering if that has a bearing on your time scale of sensitivity, because
Right.
you have different regions. I mean, why would you expect them all to have the same time?
That's right. So I think this works best if you've got reasonably homogeneous land cover. So because this variability appears to be dominated by the forests, using a mean turnover time that's dominated by the forest as well probably works best. But it might well be that actually the processes that lead to dieback do have different timescales than the processes that lead to accumulation. It's much easier to get rid of carbon actually from the system than it is to accumulate it. So there may be a reason for this. But at the moment I can't work out how to get this model to fit without telling it where the turnaround is. And I suspect there is a way to do it. It's not a strong nonlinearity because you've got two very large fluxes, and it looks like the CO2 flux is just slightly not sub that logarithmic form, and that's what does this. So it might be we can come up with a more general thing. It might just be you can't get this with this rather simple linear stochastic model approach. Who knows? We'll see. Okay, so it fails to predict that strong nonlinearity. We are trying to extend it a bit and hopefully make it general. I mean, the idea is if you could fit all the climate models, which are kind of realizations of the possible real world, some realizations, and we've got ensemble members from Ben Booth's runs at the Hadley Centre as well, then, and we can relate something in the observational record to something about the future, then the climate models tell us that general relationship between the observation and the future, and then the observations tell us where to read off the graph, right? And that's the idea, is that the models in their entirety tell you something generic that allows you to interpret the observational record. So the idea would be that we could estimate the climate impacts on tropical land carbon just from the Mauna Loa CO2 record. And I take your point, this is not just about the Amazon, this is the whole land carbon in the tropics, and provide constraints on carbon cycle projections. Questions? Right. So that leads on to the next thing. It might be, of course, that we just can't do it, because when you get this... Yeah.
Just one brief question. Can you go back 2 slides? And I'm going to ask a statistician's question.
Oh, don't do that, John T.
Simply that the land carbon in the Hadley Centre model is half that in the other 3 models.
Yeah.
Is that the only thing, or is that something we can just ignore with impurity?
It's a surprising thing, actually, because these models have generally rather weaker tropical forests, so they must be extremely tall. This is underdoing it a bit, but these are overdoing it a lot. It does relate to Matt's point, of course. This model would saturate quicker. You go down here, you can only go down here so far, and then you run out of carbon. These models, some of these models, like the Lawrence-Livermore model, has a huge CO2 fertilisation effect, which is why it just keeps on going up. So basically, the CO2 is always dominating the climate effect.
I see. So they might have started from the same point a long time ago, but if the fertilisation effect is higher, then we have a stronger response over the industrial period.
Yeah, that's right. And in fact, we can rule out now from things like free air CO2 enrichment experiments some very high fertilisation effects, which has a knock-on. That means if you want to fit the observational record, you also have to have a lower climate sensitivity of the carbon cycle. So there's another constraint on the long term, but it's not very strong. Okay. Right, so if we can't do it through these linear stochastic models, and I'm not giving up on that yet, can we do it by seeing this whole issue as a possible climate tipping point? And this is a very brief thing that I'm going to just discuss at the end. And Tim Lenton spoke about this, so Tim's the expert on this. There are a number of possible tipping points in the climate system. Regime shifts, they might be bifurcations in the mathematician's language, there might be state changes. There may just be changes that are abrupt compared to the forcing. So there's a whole load of these here. The one we're looking at is this dieback of the Amazon rainforest possibility. And this is a model derived concern, really. And the data that we're getting now gives us some constraints on this, but it's basically, we must remember, it's basically, we've only seen it in models, and in very few models actually. This is a slide I stole from Tim's talk earlier in the program, just to explain why you get these signals. So you imagine you've got a system here sitting in a relatively deep and stable state. It's oscillating around, and the size of the oscillations, so the variance, will depend on, will tell you something about the stability, how steep-sided this potential is. As you approach a bifurcation, most bifurcations, this will flatten out, and that tends to mean longer oscillations and more autocorrelation. So basically what you're looking for is what's called slowing down in the system and increasing variability, but you need both, and it's quite easy when you look at time series analysis to get one and think, oh, I've seen something. I think it's quite unusual to get both in systems that aren't going through this sort of bifurcation. This is a simple model of a bifurcation, but it turns out to be quite useful at certain aspects of the climate system. So we'll look at these two. So let's take our record. This is now from the Hadley Centre model. And so this is the land uptake again in the tropics. So you see this is what is called dieback. So a small sink for carbon becomes a strong source. The forest is lost. But again, there is a huge ENSO type variability in the system. And in this case, when you look at these precursors, you get rid of all of the signal and you say, or all of the trend, and you just say, the only thing I really care about is the variability about that trend. So if we do that, take the red from the white, we see this, and you can already see an increasing variance here, right? So the dieback in the dynamical run occurs about 2050 here. The question is, do we see increasing autocorrelation as well as would be required for that model? This is what we find when we just do that. So there's AR1 coefficient. So this is promising. There's a very strong upward trend here, but it stops before the dieback occurs. The dieback actually occurs about 2050 here. And as you can see from the time series, maybe not surprisingly, the standard deviation goes up. So the variance is going up. The AR1 goes up, but it seems to peak and come down. And initially we thought, yeah.
I'm not sure I quite understand. So you've done this on the raw scale, not the log scale. Although the underlying series is exponentially increasing.
You have to explain what you mean. I do know the terms log and exponential, but nothing else.
Linearly trending, but you've done it in
Yeah.
subtracting rather than taking a ratio, even though the series itself is strictly positive and strongly increasing.
It's not strictly positive. I mean, I'll just mess this
The
up.
underlying series.
Which underlying series do you mean? I'm going to go all the way through. Just keep talking, John, because I have to.
Funny thing happened to me this morning. I went to work.
Yeah, so the land carbon sink, so that's the rate of carbon uptake in each year, the amount of carbon uptake in each year has this huge variability in it.
Right.
So it's not strictly positive. The decadal, this is one more, no, 10 more. God, I've spoken too long. Right, we're there? Yeah, so if you look at this, the zeros here, Jonty, so this thing's going, I mean, basically the land carbon sink of the tropics is mostly noise. You would imagine, I mean, it's just a huge amount of variation. And we worry about this bit here, but the question is this residual telling us something about whether we've got a tipping point or not?
Right. So
Does that make sense?
About tipping point is about the structure of the changes in the series and not the structure of the series itself.
I'm going to say yes, but that's something we might debate because I think there is an issue with these whole approaches that others may be able to comment on of whether you've really, whether what you have to do to detrend. I mean, all I've done here is to take decadal means, which gets rid of the ENSO variability, and then look at the variation about that. But you could argue, of course, you need to do other things to detrend the data as well. This is a standard way to do it. Tim, yeah?
If the variance was related to the signal, and as the signal went down, the variance increased, you get exactly what you're getting there, and that's nothing to do with tipping points. That's just to do with the structure of the series.
So how would that, so that's if, okay, so if the variance was fractional, oh, that's what you're saying, Jonty. So if the variance is, yeah, and there is an element of that, but it's not, there's no reason to believe that, I'm going to try and be coherent just for a second. There's no reason to believe that this would be a fractional variation about that mean. It is a fractional variation about what's called the net primary productivity, which is the photosynthesis. Okay, so if the photosynthesis grows, you would expect to see the variance grow as well, even if the fractional variance doesn't change much. Does that make sense? Probably using the wrong terms here. Okay, so if the mean were growing in the net primary productivity, you would see an increasing variance just because you've got bigger fluxes, bigger counteracting fluxes. But that's not the case here. It might be the case for this early part, but for this later part, the net primary productivity is actually diving. So if I were to plot the standard deviation over the mean, that would be really going up. So an interesting point there. Well, maybe I should do that. Maybe I'll see a stronger signal in that case.
It does look, though, like your signal variance is increasing.
Yes, it's certainly increasing. The question is that, I guess what you guys are saying is that a consequence of the change in the mean state? And I don't think it is. But I guess, how would we decide whether it was best to use the absolute values or some scaled value related to the mean? I mean, this is one of the things this whole thing's a bit... Yeah.
I guess the question is whether the Amazon dieback in your model is really a bifurcation.
Yeah.
Sorry, can you repeat the question?
No, I guess the question is whether the Amazon dieback in that model is really a bifurcation.
Oh, it's a bifurcation.
And
it seems to be.
Well.
It seems to. Well, to answer that, we've actually Renata Vitola, who you may know from who was here earlier in the program, has developed a very simple two-equation model for this sort of response. And it's a rather basic type of bifurcation, but if you take that simple model, you do see these sort of signals. And it might be that you don't need a very complicated bifurcation to get sort of this sort of behaviour. Just need to change the state somewhere, I guess. Yeah.
But Peter, what I'm hearing actually is that you're looking for evidence for a bifurcation, and everyone else seems to be asking you, can you falsify a bifurcation? Can you come up with a test in which there is no bifurcation?
Right. I suppose what I'm saying is I'm not sure I care whether it's a bifurcation or not.
Okay.
I mean, just whether there is a signal in this particular model that you can see before you see the mean state change significantly. And my suspicion is that, as I was sort of trying to imply, that I don't think it needs to be anything very clever here for this sort of response to occur in the system. I imagine we can come up with things that haven't strictly got bifurcations that would do the same sort of thing. It may be more general than just bifurcations, I suspect. Tim, yeah?
Yeah, I mean, just coming back to this point about the dieback in the Amazon being related to changes in precipitation.
Yeah.
I mean, does that, if you ran the Hadley model without any kind of carbon cycle interacting with carbon, does it still produce the same shift in the rainfall patterns over Amazon?
Yeah, it's similar. It's amplified by the vegetation, but the basic driver is an SST pattern.
Because then I was thinking, you know, if you're really looking for the mechanism, you really should be looking for, I don't know, bifurcations or some regime shift in the circulation patterns, rather than the...
Yeah, and I guess, sure. So there are two parts to this. In a sense, if you go down this route of, I agree with you, if you're interested in the mechanistic drivers, that's what you do. And I think, it's not here, Valerie's here. I mean, Tim Lenton was looking at AMO variation, I think. Is that right, Valerie? So we're starting to apply these approaches maybe to time series of SST indices. Again, it doesn't give you a mechanism, it just tells you there's evidence for some kind of tipping point in that part of the system. In this case, it's a sort of pragmatic thing really, Tim. We're just saying, well, let's say we can't, well, I don't think we're ever going to be able to predict this bottom up. Would we be able to find a signal that potentially could be measured that would give you a warning at least? And if these work, these give you quite a lot of warning if they work.
How do you use the sort of plots that I've seen Valerie producing the colours?
It's potential analysis when you can say about the bifurcation in the number of states. Actually, I was thinking that we could compare autocorrelation for raw data and for residuals to conclude about whether it's transition or bifurcation.
Right, you can tell the difference.
Yeah.
Right. I better, how are we doing for time? Oh, not too bad. All right, so when we look at this, so this in a way is a bit frustrating because this looked like the signal of a forthcoming bifurcation, but it seemed to occur too soon. But then I remember there was a paper by Chris Jones from the Hadley Centre where he'd looked not at the dynamical evolution of the carbon in the Amazon, but at the equilibrium state. So what you do is you take the model and you say, if I'd frozen the climate at this time, this CO2 at this time, what forest state would I have got? And he finds a bifurcation or a transition from the forested state to a rather steep decline to savanna state at around 2000. So in that model, it's the same model, there was essentially a commitment to change around 2000. So maybe what we're picking up here, and I'll just clutch for a moment at some straws, is the signal of the change in the equilibrium, and which is what you might expect, rather than the dynamic. In which case, for slow systems like the forest, relatively slow systems, you potentially get even more warning, right? Because even if we carried on this path without taking account of this, the dynamical change would not have occurred till about 2050, just because it takes a while even for the carbon to come out. Right.
So what you're essentially saying is that past that point, changes are irreversible. You have gone the other way of the
yes. I'm not sure whether they're not strictly irreversible, because you could, no, they're not strictly irreversible. There's just a long lag in the system. Dave?
You started by saying when you go through the tipping point, the variance would increase or whatever as you go through the thing.
Yeah.
Your diagram there shows the variance carried on increasing after the...
Yeah, that's interesting,
How do
isn't
you
it?
explain that in terms of potential?
Well, I think the point is that if you just got a variance increase and you didn't have a change in the AR1, then you haven't got a signal of a tipping point by this simple model. So I think it's only when you've got both that you've got a chance that you're seeing something like that. And that's why you need to check both, because I looked just based on other papers just at the AR1, and you can get AR1 trends all over the place, right? But they're not very often associated with an increase in variance. Right, so Chris and Tim Lenton and Valerie are looking at spatial correlation now, because this in a sense is rather crude. We just say take a single time series, what does it tell us about whether we've got a bifurcation coming? Actually what they're finding, I think, Chris, I'm going to paraphrase, is that if you look at the spatial correlation, you also see a kind of explosion of spatial correlation as you approach the tipping point. And the question is, would that in combination with the temporal correlation give you a more robust signal, or maybe an earlier one? And I think there's good reasons, particularly with short-range interactions, for example, vegetation feedbacks, for that to be the case. You'd expect to see things like that. We're going to test for this slowing down as a forewarning of Raman dieback in a whole range of ensemble runs. Ben Booth did what's called a carbon cycle ensemble, so he took the HADCM3 model that has the dieback and just fiddled with the land parameters and got a whole range of diebacks and some that don't die back. So the question would be, if he gives me those time series, can I tell him which ones die back and which ones don't? And then Renato Vitolo and Pete Ashwin at Exeter have been developing these simple models to demonstrate different types of tipping points, not just bifurcations, rate-dependent ones. So that the idea is we'd have a simple model or a couple of simple models where we could demonstrate these and look at their precursors. And that's it. Thanks very much.
Well, we've had some excellent questions and discussions so far, but we have time for a couple more. If anyone has any.
Must be coffee time.
No.
Is it not?
No. I've got to work a bit more for you. I'll try one while we're waiting then. So you found a simple model that fitted the carbon uptake in a number of models.
Yeah.
The worst fit was for the Hadley Center model, where you had to choose a really small time scale to get the fit. And that's not you believe, not an accurate reflection of the real world, but could it be an accurate reflection of the behaviour of the Hadley Center model? Telling you something about the model.
Yeah, I think this is a leading question. You want me to say that the model I developed is inaccurate? It's a tipping point to a note. I think it may be an accurate reflection of the fact that there is the rates of loss of carbon are different from the rates of accumulation. So, for example, in this model, there's a Lotka-Volterra type of non-linearity in the way the vegetation coverage changes, and that basically means it goes down fast and it goes up, and it may be partly that. But my suspicion is that actually what we're seeing is a saturation of the CO2 effect. And the thing about the Hadley model is because it has these strong feedbacks, it has much higher CO2 than the other models, so it gets to the saturation, and I therefore think this logarithmic form doesn't quite do it. So I haven't found anything generic enough to fit all the models, so at the moment I'm just grappling with that.
Tim?
I just come back, because just explain this to me in very simple language, because I'm still a bit confused. Coming back right to your very early point about MEP. I mean, if I have a sort of a stationary Earth, then the heat will sort of transport to the pole through some mega Hadley cell, basically.
Right.
And as I start to rotate the Earth, eventually I'll reach a stage where I can generate baroclinic waves, and that heat transport then is going quasi-horizontally. I mean, it's a fundamentally different mechanism. So you made some statement that, so these are all potential Earths which are rotating more slowly than the current Earth is rotating. But you made some statement that this heat transport didn't depend on rotation. I just find that a kind of a difficult concept to grasp when you think about this transition from one type of dynamic to another.
I suppose the argument would be, and this won't make it any easier, is that the system has a dynamical structure that allows it to maintain this maximum entropy state. And when there isn't a dynamical structure that can do that, then it won't be at the MEP state. So in that simple model, what you find is if you push the rotation rate a bit more, suddenly the MEP state that doesn't take account of the dynamical constraints wouldn't be realistic. But at least with that simple model, you're not quite there on Earth, which is why Partridge got away with it. But it also means that the Earth was probably in a slightly different... It would be very interesting to look at whether, when it was spinning a bit faster, whether there's any evidence that the structured atmosphere was any different. That'd be a long time ago, though.
But just to elaborate on that point, though, that doesn't mean that the MEP principle would not apply. You just apply it differently.
Yeah. There comes a point, though, when there are so many constraints that the MEP simplification doesn't help. So, yeah. I mean, it's sort of whether the constraints are very significant compared to the MEP state itself.
One last question from the back.
Yeah, well, this is I agree with Tim that is a big problem of these models, and we have the same in the thermoline circulation models that consider only Z and Y and do not have actually the Gulf Stream.
Yeah.
And so they really don't contain the dynamics of the Earth as we know it, but somehow they can go without.
Yeah.
And this is why at this stage, I think in the thermoline community from oceanic and spatial, we try not to look at the result of these models, but we try to implement a little bit more complex models that consider the dynamics, so the Gulf Stream. So most of the thermoline circulation models, Y and Z, do not have that. But still, you might say they reproduce the thermoline circulation of the ocean.
Yeah, and people have applied actually MEP principles to changing the THC state in three-dimensional models and found that some aspects of the MEP formalism allow you to predict when that would happen in a model. So I don't think we see that as an alternative to complex models, no way. It's just that we might be able to understand some aspects of them that are robust. And in some cases, we might even be able to provide parameterizations that are have minimal number of parameters. But I accept it. The great thing about this is it's mysteriously effective. You can take almost everything out, and in a lot of parts of these systems, it still does a reasonably decent job. And I think that's telling us what... And in a sense, you're only really looking at heat fluxes, right? Basically, all you're saying is that the heat fluxes are not strongly constrained by this. Doesn't mean everything else isn't. I mean, hydrological patterns, salinity patterns in the ocean, you would expect them to be dependent on the dynamics, but the dynamics may itself be almost a diagnostic of that MEP heat flux. I'm going to leave it there because that's a good time.
We ought to move on. Thanks again, Peter.